said, my knowledge of quantization is also rather limited. It's just
So please, everybody, back to your seats. All right, so we have the third speaker of the afternoon. So let's just check everything is okay with Professor Zhao from Beijing. Can you hear us?
Yes, I can hear you. Yes.
Okay, and we hear you perfectly. You're a little bit a strong light behind you, so we cannot really see your face, just your silhouette, so to speak.
Okay, no problem. Okay.
That's okay. And we have your slides, everything works fine.
Okay.
So it's a pleasure to introduce Professor Zhao from Beijing. And we will have another talk on nonlinear PDEs, Schrödinger equations, and waveguide manifolds. Please go ahead.
Okay, thanks for the introduction and the invitation. It's my big pleasure to give an online talk at this wonderful workshop. So my topic is the dynamics of nonlinear Schrödinger equations on waveguide manifolds. I hope in future I will be able to visit Mexico. Let me very briefly introduce myself to the audience. I did my PhD with Benjamin Dodson at Johns Hopkins University. After that, I did my postdoc at the University of Maryland with Professor Grylakis and Professor McDown. And now I work at Beijing Institute of Technology, Beijing, China. Here's the plan for this talk. I will very quick overview my research, and then I will talk about the background and motivations for the topic of NIS. NIS is short for nonlinear Schrödinger equations on Euclidean spaces. Euclidean spaces is very fundamental. People consider NIS on the Euclidean spaces first, and later people may replace Euclidean space by some other spaces. I will give a general overview. And then I will talk about some classical results and a few of results that I have done for this research line. And finally, I will talk about some recent progress and give further remarks. That's the plan for this talk. Yeah, about my research, there are four research lines that I have been working on. The first one is nonlinear decay of NS. It's based on the collaborations with Stefani, Kilip, Vishan, and Fan. So we consider NS. We want to investigate the nonlinear decay property for the solution. And the second one is NS on waveguide manifold Rm cross Tn. So the semi-periodic space, product space Rm cross Tn is the so-called waveguide manifold. We replace the Euclidean space by the product space. And the second one is today's main topic. And there are several things we can study. We can study the streetcars, bilinear streetcars, and use them to establish the local Villers-Posny theory. And we can study the long-time behavior like scattering. It's based on the joint works with Yannick Serre, Haitian Yue, and many other professors. The third research line is about many-body equations, many-body problems. It's mainly based on the collaborations with my postdoc mentors, Grylakis McDown. And the last one is about stochastic NS. And all of the four research lines have some interactions with each other. Today we will mainly talk about the second one. And I have listed some recent works I have done for each research line. So on this page is about the first one, the nonlinear decay of NS. We want to say something about the decay property of nonlinear solutions. And all of those results are tightly related to the classical long-time theory of NS. For NS, we have some scattering results, and scattering means that the nonlinear solution resembles linear behavior in the long run. And on the other hand, we know for the linear solution, we have dispersive estimate. So dispersive decay estimates plus scattering suggest us we can study the dispersive decay property for the nonlinear solutions. So that's the basic idea. And for this page is some of my works on the many-body problems. Like we study the HFB system. This topic is also related to NS. We need some dispersive techniques to study many-body problems. And on the next page, I have listed some of my results on today's topic as on waveguide manifolds. So I have, with collaborators, I have studied Valposenitz scattering and the resonant system, and also some bilinear estimates. Finally, on this page, I have listed two of my results on the stochastic NS. Okay, so now I will talk about NS on Euclidean spaces. And after reviewing this part, we will move on to the waveguide case. So we consider NS in the defocusing case. We consider initial value problem 1. It's a power type nonlinear Schrodinger equation. It's in defocusing case, it means for the nonlinearity, the sign is plus. If we add a minus sign, the problem will become focusing. And for this initial value problem, we have a scaling invariance. If U is a solution, after a scaling transformation, we get another solution. And this scaling invariance naturally defines the notion of criticality. So the criticality means that if we say the equation is H dot SC critical, it means this norm is invariant under the scaling. It's easy to check that if the power P, the dimension D, and the criticality satisfies a certain relation, then the problem is H dot SC critical. And typically, if SC equal to 1, the problem is energy critical, because H dot 1 is corresponding to the energy conservation. And when SC equal to 0, it would be H dot 0, which is just L2. And the problem is also called mass critical, because L2 critical L2 is corresponding to the mass conservation law. And for such an initial value problem, we are interested in the Valposenitz theory and the long-time dynamics. For the defocusing, important long-time dynamics is called scattering. Scattering means that in the long run, the linear solution, the nonlinear solution resembles linear behavior. But if people consider the focusing case or the supercritical case, the dynamics will be more complicated. In terms of scattering, there are many classical results. And here, let me do a very quick overview. For the energy critical case, mass critical case, and the case when criticality equal to 1/2, the problems are all solved. People know how to establish long-time large data scattering results. For the energy critical case, Beijing have established large data scattering in 3D with radial assumption. At the same period, Greylakis did the large data global Valposenitz results. And later, I-team generalized Beijing's result to the non-radial case in 3D. And later Rickman Wei Shang did the 4D, and Wei Shang did the 5D and higher dimensions. So it's all solved. For the mass critical case, the large data scattering is also solved by Dodson. Dodson has 3 works on this topic. One is for 1D, another one is for 2D, and the other one is for 3D and higher dimensions. When the criticality equal to 1/2, there are 2 models, 3D cubic NS, which is done by Koenig-Miller. Another one is 2D quintic NS by Xueying Yu. With the establishment of the scattering results, people developed new methods and techniques, such as interaction Morrison estimates, I method, energy induction method, concentration compactness, and the long-time Strikers estimates, and so on. In fact, if we want, we can summarize the scattering results by a very natural conjecture, the so-called critical norm conjecture. This conjecture is formulated like this. We consider the H.SC critical nonlinear Schrödinger problem, and we assume the critical norm stays bounded in its maximal lifespan. Then we have global well-posedness and scattering. Here's a quick remark for this conjecture. So the idea of critical norm conjecture is uniform boundedness of the critical norm implies scattering. In other words, there are no type 2 blow-up solutions. Type 2 blow-up solution means that the critical norm stays bounded, but the scattering norm blows up. The solution does not scatter. And for the 2 special cases, energy critical case and mass critical case, we do not need this assumption because the conservation law automatically did the work. We do not need to worry about the critical norm. They will not blow up because of the conservation law. But for other cases, it's not clear. We still need the critical norm assumption. Yeah, all of the classical results we have mentioned can be summarized by this conjecture. And this conjecture has been studied by many people, like Bergin, Greilakis, ITIM. ITIM is a very important team in dispersive PDE. They are Colander, Kiel, Stefanani, Takoka, and Tao. Koenig, Miller, Katie Wishang, and many other people. Yeah. And as we just mentioned, for the mass critical case and energy critical case, the conjecture is completely solved. But for the general case, like the intercritical case, when SA is bigger than 0, less than 1, is not completely solved. And for the energy supercritical case, when SA criticality SA is bigger than 1, is also not that clear. Here are 3 quick remarks. The first one is for the focusing case. For the focusing case, people can formulate a similar conjecture, which is known as ground state conjecture. For the focusing case, we have ground state structures. So for the focusing case, the assumption 4 is not enough. We not only need the critical norm stays bounded, does not blow up, we also want the critical norm stays below the ground state level, So we need to do a replacement. And under such a ground state assumption, people can prove some scattering results. So that's the meaning for this remark. For the focusing case, we have ground state conjecture. For the second remark, in fact, people can naturally formulate a dispersive decay conjecture. We know scattering means the nonlinear solution resembles linear behavior, and for linear solution, we have dispersive decay. So putting the two things together, we conjecture that the nonlinear solution also enjoys the dispersive decay. And for the third remark, people can study quantitative scattering. So usually when we are talking about scattering, people cares more about usually people cares about qualitative. That's already okay. We know the long-term behavior, but people can also study the quantitative scattering, which means we can, for example, if we can control the scattering norm of the solution by the size of the initial data. Another direction of improvement would be, can we remove the critical norm assumption? For example, for 3D cubic NS, just prove large data scattering in H dot 1/2 the critical space without critical norm assumption. This is also very interesting, but maybe very challenging, maybe very hard. Okay, so after overviewing the Euclidean case, we will move on to the waveguide case. So now we replace the RD by RM cross Tn. So we consider the waveguide manifold. We consider the formula initial value problem 5. And for this initial value problem, there are also many things we can study. The first one is the estimates. If we consider Euclidean case, the estimates are well known, like the dispersive estimate, streetcast estimate, bilinear streetcast, more or less. But if we consider a new space, like a new manifold, it's important to investigate the estimates at the first glance, and there are still some problems left. For example, for the streetcast estimate on the waveguide manifold, there are still some open problems left. And after we have the fundamental estimates, people can study the well-posing theory together with some new function spaces, which may be different from the Euclidean case. And based on them, people can also study the long-time behavior. For example, like the scattering behavior we just mentioned, because the waveguide case have some Euclidean components. Euclidean components gives us some dispersion, so there's still some hope to prove scattering. If we consider the pure periodic case, we consider the case TD, scattering is not expected because we do not have dispersion. So waveguide case is like an intermediate point between the Euclidean and the periodic. It's still possible to study the scattering for some typical models. And to study these topics, we need to combine the techniques and the tools from both the Euclidean case and the Taurai case. Many people, many professors have done a lot of works on this research line as on waveguide manifolds. I just mentioned some names: Tataru, Her, Koch, Zivadkov, Takoka, Anescu, Poseider, Hani, Stefilani, and more people have done the work if we consider the Taurai case. MS on Taurai is a famous research line in the area of dispersive PDEs. For this, here's the outline for this part. So first, I will give an overview for this research line. I will talk about the strategy, the classical results, and what's the difference between the NS on waveguide manifolds and the NS on the Euclidean spaces, and also the toric case, what the relations, what the differences. And then I will mention work by Hani and Poseider. They have a scattering result for the waveguide case. And to talk about this research line, basically there are two natural ideas. The first one, there are still some good and deeper problems in this research line. One can further investigate. For the Euclidean case, the theory are very complete. And if one can think about if we can generalize some Euclidean analogs to the waveguide case. And the second would be one can also compare the waveguide case with the toric case. For the toric case, there are many classical results. And for the waveguide case, we now have the Euclidean component, we have dispersion. Can we get some better results than the toric? And furthermore, one can try to apply the techniques, the methods in this research line to handle some other dispersive models. In other words, people can study some other dispersive equations in the waveguide setting. Okay, so here I will talk about, I will mention some classical results in this research line, some of the important results. So due to 1990s, Bergin have done a series of important works on the topic of streetcars for NS on the toric, based on the analytic number theory. He used the circle method and obtained the streetcars estimate with a partial range, according to the most recent results. And Bilk, Jarrah, Zvelikov have done works on the topic of NS on compact manifolds. And the group of Her, Tataru, Zvelikov have done two works published on Duke and Krells. One is for the waveguide, one is for the toric. They study the critical NS on toric and waveguide respectively. They use the new function spaces which are different from the Euclidean case, and they can prove small data global hypothesis. And after their work, the group of Ionescu Poseider, they also have two results correspondingly, one for waveguide, one for the toric. They generalize Her, Tataru, Zevalikov's results to the large data global case. They have large data global hypothesis. The main idea would be they generalize the profile decomposition and some other Euclidean techniques to the waveguide case and the toric case. And after that, Hani Poseider has a work on the scattering for NS on waveguide manifold. In particular, they study a typical model, a quintic NS on R cross T, R cross T2. They have scattering results. And the last one I want to mention would be Bergin Demeter's famous result. They use the decoupling, the L2 decoupling method to get the streetcars estimate for NS on toric. And later Byron extended this result to the waveguide case, also using the decoupling method. And a long time before Byron's result, I want to mention is Takoka Zevalikov's work on the streetcars estimate. Takoka Zvelikov proved L4 streetcars estimate without the derivative loss on R cross T. So R cross T is two-dimensional waveguide manifold, which is very special. And a long time ago, without decoupling, people develop Takoka develop have a streetcast estimate for across T. Honey Procedur's work is representative to some extent because it combines almost all previous tools and ideas with modifications. In fact, to prove scattering, they also used the function spaces in her Tataro Zveladkov, and they used the idea of profile decomposition in Ionescu procedure. So their work combines the important techniques in previous papers. And the second one would be this result is the first scattering result, large data scattering result for the waveguide case. Before this result, people only have global well-postingness results, not scattering. And there are also some new ingredients in their work. The first one is global in time streetcast estimates. Before their work, people only have local in time streetcast estimates. But we know that to study scattering, global in time streetcast estimate is very important to describe the long time dynamics. And it's also, in some sense, it's also very is somehow expected because for the waveguide case, we have the Euclidean components, and the Euclidean components gives us some dispersion. That's why we expect long time global in time streetcast for the waveguide case. And the second one, they can reduce the scattering problem to a scattering of a resonance system from waveguide to resonance system. It's also a new ingredient. And many scattering results for the waveguide case have borrowed the idea from this paper. Okay. For the waveguide case, we also have the conservation law, and the scattering is in the Euro sense. So we consider scattering, which means in the we have final states, V plus minus, and in the long run, the nonlinear solution resembles linear behavior. Okay, so next we will briefly summarize the scattering results for the waveguide case. So now we consider the diffusion case. If it's the Volker case, there are also some results, but let's talk about the diffusion case first. Based on the existing results and the theory, it's highly expected that the solution scatters in the energy space if the nonlinear exponent p satisfies a certain range. So p is not less than 4 over m, and p is not bigger than 4 over m plus n minus 2. So let me very briefly explain what the meaning of this range, what the heuristics about this range. So if we consider the H1 scattering problem, we need the problem to not to be energy supercritical and energy and mass subcritical. So we need a range. So the meaning for the right inequality means that so m plus n is the whole dimension. The whole dimension of the waveguide manifold is m plus n, and we have 4 over dimension minus 2, which is the energy critical exponent. So p cannot be bigger than that number. So in some sense, we can just regard the Tn to be Rn. So we need p satisfy this inequality. And for the other part would be, we can, in some sense, we can just ignore the Tn ignore the Tn. So the problem is posted on Rm, and we need P to be bigger than 4 over M. So the problem cannot be mass subcritical. So that's the idea for this range. In fact, if we want to add more assumptions on the initial data, it's possible to enlarge the range a little bit. For example, P can be less than 4 over M. Maybe P can be bigger than 2 over M. That will be enough if we give stronger assumption, initial data assumption. Like consider the weighted initial value space. And if P is bigger than 4 over M plus N minus 2, we need some more regularity assumption. It's also possible to do something. Here's a remark. So most of the global results, NS on tori, NS on waveguides, are regarding the defocusing case. And in general, the dynamics are richer in the focusing case. And shortly, we will talk about the focusing case. There are some recent progress on the ground state conjecture. For the focusing waveguide case, we can also formulate ground state conjecture, and there are some very recent progress in this direction. And for the defocusing case, we can summarize some existing results. So we consider the low dimensions first. The whole dimension is not bigger than 4. If the whole dimension is bigger than 5, the nonlinearity will be fractional, and it will be more complicated technically. And we want the nonlinear exponent to be integer, and the dimension to be low, not bigger than 4. So and then we consider the inequality into consideration. We put the P bigger than 4 over M and not bigger than 4 over M plus N minus 2. If we consider all restrictions, we can list all of the models. There are especially 11 models. When N equals 0, so we consider Rm cross Tn. When N equals 0, the problem is pure Euclidean. And for Euclidean problems, the results are well known. The scattering results in H1 are well known. When N equal to 1, there are 4 models, R cross T, R2 cross T, R3 cross T, R2 cross T, with cubic and quintic nonlinearity. And all problems are solved after the work by Hani Poseidor. And when N equal to 2, there are exactly 2 models. Cubic NS on R2 cross T2 and quintic NS on R cross T2. So it's a quick summary. So now for the defaulting case, the scattering results for the low dimensional waveguides with integer nonlinearity are all solved. And the next step would be people can extend this result to more general models. For example, we can consider higher dimensional waveguide with fractional nonlinearity. There are some more problems can be further investigated. And then we can talk about the main strategy for the waveguide case, how to achieve large data scattering. In fact, the general idea is still similar as the Euclidean case. The proof follows from standard machinery based on Koenig-Miller's works, concentration compactness and rigidity. So the first step would be we need to have some preliminaries. We need some good estimates, good function spaces to to do the local verbosity and small data scattering. And after that, we can use Koenig-Miller's machinery concentration companies to generalize the small data scattering to the large data scattering. Yeah, so the main strategy would be speaking, there are some new ingredients. The first one would be the function spaces. People use new function spaces different from the Euclidean case. And the second one would be the streetcast type estimates. In fact, streetcast estimates are not that easy compared to the Euclidean case. Decoupling method are needed. And then we need Euclidean profile or some approximations. So according to the scaling structure for the waveguide case, people can use some Euclidean scattering results like black box to do some approximation. And the last one would be the profile decomposition. The profile decomposition for NS in different settings, Euclidean, Tori, waveguide, and even some other manifolds are often different. The profile decomposition highly depends on the geometry. For example, for the streetcast estimate, we can compare the Euclidean case and the waveguide case, Tori case. They are very different. They are very different. For the Euclidean case, we know the streetcast estimate is like this. There's no derivative loss, and the estimate is global in time, which is very good. And for the waveguide case and the Tori case, the estimate is like the following one. Is like the estimate 7. If we consider the Tori case, usually there's an epsilon loss, and the estimate is local in time. We refer to Bergen's work and Bergen-Demeter's work, and also Caleb-Vishant's work. If the exponent p is apart from the endpoint, Caleb-Vishant have a method to remove the epsilon loss. But if p equal to the endpoint, there's an epsilon loss, and the estimate is local in time. For the waveguide case, first we can recover the estimate 7 for the waveguide case with the same dimension. We refer to the work of Byron. And for the waveguide case, there are some points which are better than the Tori case. The first one would be we can derive global in time estimates. We refer to Byron's work, and also the work we just mentioned, the Hani-Poseidon work. They also have global in time estimates. And the second one would be for some special case like R cross T, the streetcast estimates do not have derivative loss at the endpoint. We refer to Takoka-Zhevatakov's work. So there are still some differences between waveguide and Tori. So the general idea would be the Euclidean case is the best, global in time, no derivative loss. And the waveguide case is like between the Euclidean case and the Tori case. And there are still some problems left. Okay, and now we give more remarks on the comparison between Euclidean and the waveguide case. So the function spaces are often different. For the waveguide case and Tori case, we use the UP-VP spaces based on atomic spaces, variation spaces. We refer to Koch-Tataru's work. And after this work, many works by Her, Tataru, Zhevadakov, by Ernest Poseidon, they all use UPVP type spaces to deal with critical NS on waveguide and tori. And the second difference would be streetcast estimate, which we just mentioned. If we want to study scattering, global in time streetcast estimates are very necessary, very important. And the third one is the Euclidean profile approximations. And the next one is the profile decompositions. For the Euclidean case, we refer to Karani's work and Kenyon Miller's work. And the last two comments would be, if we consider scattering, not for all waveguide models we expect scattering. It depends on the distribution of the R component. Emphasize that we consider H1 data for convenience. That is because we have the waveguide case, and there are two extreme behaviors under the scaling. For convenience, we can explain it in this way. So one extreme behavior is like we can just regard the tori component to be the Euclidean components. That's one situation. For the other extreme behavior is that we can just ignore all tori directions. And that's why we need to consider the H1 inhomogeneous space for convenience. If we consider the H dot 1, the problem will be more difficult and the space is not natural enough. So for all the works I have mentioned, they consider the H1 space. And next, I want to make some remarks on the conversation between defocusing and focusing. For the Euclidean case, we already mentioned that focusing, defocusing, they can be very different. In general, focusing case is more complicated. The dynamics are richer. For the waveguide case, the people can also study the focusing as on waveguide manifold. So for the focusing case, we need to make proper assumptions. Proper assumptions means that we need the initial data satisfy some ground state assumption. It needs to be below the ground state, and we need some variations. Do some variational analysis to investigate the ground state structure, and do some energy trapping argument to extend the below ground state property from the initial data to the whole solution to do some energy trapping. And for other technical tools, there are also some difference, like the moralized estimates, how to use it. For the focusing case is very important. And also the rigidity argument would be different. In recent 2 years, there are some recent progress on this research line, focusing on waveguide manifold. We refer to the work by Cheng and his collaborator, and the work by Yongming Luo. He has some results on the focusing case. Okay, next I want to make more remarks on related problems. In fact, at the very beginning, I have mentioned that there are 3 types of problems people can study which are very natural. The first one is the estimates in the waveguide setting. The second one is the hypothesis. The third one is the scattering. In fact, there are more problems people can study for the waveguide case. For the first one, people can study other dispersive equations on waveguide manifolds. I have seen some papers about other dispersive equations in the waveguide setting, such as fractional NS, wave equation, and Klein-Gordon equations, and KP1, KP2. They all have results in the waveguide setting. And the second one, people can study problems rather than GWP and scattering, such as the descriptions of the dynamicals of threshold solutions, using a method to get some results, and study the weak turbulence, growth of Sobolev norms, and study the resonance system related problems. And people can also study the analysis problems. Just consider the linear solution, study the Strickhaus estimates. It's also very important. It's also very interesting. The third one would be, we know that for NS, the random data theory is very popular, and there are already a lot of works. And for the waveguide case, people can also combine stochastic and together with NS on waveguides, like do some random data, do some randomization for the initial data and get some large data while posting its results. And there's one work on this topic. And the next one would be the decay plus NS on waveguides. So we know that for NS, people can investigate decay. For waveguide case, it's also possible. Although waveguide includes the tori direction without dispersion, but it also includes some Euclidean components, which can give us some dispersion. So this gives us some room for investigate the decay. The next one would be the many-body problems. People can consider many-body problems in the waveguide setting and the tori setting. There are some works for the tori setting, study the many-body problems. And the next one would be consider the general waveguide. So what is the philosophy for the waveguide? Waveguide means we have two directions. One is Euclidean, we have the dispersion. Another one is compact, there's no dispersion. And in fact, there are some other models can be regarded as the generalized waveguide manifolds. That means the behavior is similar, and the property of the nonlinear solution is similar. One direction is free, another direction is confined. There's a trap. Yeah, it's interesting to summarize different models together, and they share some common points, and they share some differences. And the next one is the larger range. We have mentioned that people expect scattering in H1 if the nonlinear exponent satisfy a certain range. And in fact, we can discuss if the range can be larger. It's possible if we have strong assumptions on the initial data. At last, finally, I want to mention some very recent progress which is related to this line. I want to mention Clark's work, Clark and Clark-Cohn. They have some interesting works on the topic of NS on tori. NS on tori is tightly related to NS on waveguide manifold. Clark-Cohn's work studies the local hypothesis for NS on tori. They can study very general fractional nonlinearity. Before their work, as we have mentioned, previous works cares about the cubic nonlinearity, quintic nonlinearity, but they can deal with the general nonlinearity. And later, Clark did the global hypothesis, extend the local hypothesis to global hypothesis for energy critical NS on tori for higher dimensions. If the dimension is 4 or 3, the nonlinearity is cubic and quintic, but for higher dimensions, the nonlinearity will be fractional, and there are some technical challenges. And Clark also have works on the Strickhaus estimates. They proved two sharp Strickhaus estimates in 2D, which is a very interesting result. They improve the they have the sharp derivative loss, which is log n to the 1/4. This result is sharp. And based on this result, they have a new archive preprint this year. They prove global hypothesis for 2D cubic NS with HS data. S is bigger than 0. It's also a very interesting results. And for all those results are tightly related to waveguide case, we can consider can we extend those results, like apply them, extend those results to the waveguide case. It's interesting. For example, for the second work, can we do GWP and scattering for energy critical NS on waveguide manifold? It should be doable combined with some other other ingredients. And for the third one, is very interesting. People can study how to obtain the sharp three-class estimates at the endpoint. It's not very clear. The only clear case is the case R cross T by Takoka Zevalkov.
You have a few minutes left.
Okay, sure. I will finish in one minute. I will do a very quick summary. Yeah, so there are some general idea. I think this research line is very interesting. It's related to the Euclidean theory and the Tauride theory, and there are many problems left. There are some doable problems for new starters, and there are some deeper problems for senior researchers. And there are some ongoing attempts like study many-body NS on Tauride waveguides, and like do some generalized waveguide framework. And we can study the topic NS on mixed geometry, which is even more general than NS on waveguide. And the third one would be do more analysis works for the waveguide case. And do some other models, study some other problems. Yeah, I think there are still some interesting problems about this research line. Okay, so eventually, finally, it's a summary of my research interest, and today I talk about the second one, NS on. Sorry, today I just talked about the first one, NS on the waveguide manifolds. Okay, that's all for my presentation. Thanks for listening.
Thank you. Let's give a hand. I don't know if you could hear people clapping. So we have a question here from Ricardo Vera.
Well, your norm conjecture, you say, well, under the condition of the conjectures, there will be scattering, so the solution would scatter. Do you mean short-range scattering, where the solution is asymptotic to the solution of the linearized equation, or also long-range scattering, when you have to modify by a phase solution?
Thanks for your question. You mean for the Euclidean case or for the waveguide case?
Well, the Euclidean and waveguide where the norm conjecture would apply, right? So in the situation where the norm conjecture is expected to hold, my question is, which type of scattering are you referring to? Short range, long range, or both?
For the Euclidean case, I think I refer to the long range scattering. For the waveguide case, we have both. We have scattering like this. There are many scattering results after Hani Poseder's work, and they also have some modified scattering results. For example, we can consider cubic NS on R cross TD, D equal to 1, 2, 3, 4. Hani and his collaborator has a work like this. We know for cubic NS, For 1D cubic NIS, we have modified scheduling, and they can extend this result to the waveguide case. They get modified scheduling, and they have some Sobolev norm growth results.
Well, thank you.
You are welcome.
Any other questions? Yes, Miguel.
I mean, you mentioned many times about many body problem in this setting. Could you explain something about that? What is the model for many body in this case?
For many body, for the waveguide case, I haven't done a lot. It's just some basic idea. I have done something like, for example, on this page for result 4 to 6, we consider many body Schrodinger equations with interactions. So usually if the space is Euclidean, the result is not very hard. People can use the double endpoint streetcars, just treat all interacting potentials to be perturbations. But for the waveguide case and the Taurai case, we need to use some other ingredients. So I can prove streetcars estimates for many body Schrodinger equations in Taurai and waveguide. So that's my results with my collaborators. And based on this, maybe in future we can say more things about the PDE and mathematical physics. That's a future plan.
Do you have channels, different channels, scheduling channels, for example, in many body?
For many body problems, we can so usually it's posted in 3D in R3, and we can replace it by T3 and even waveguide. But waveguide hasn't been studied before, so I'm not very sure. It's a general idea for future if the problem is meaningful enough. For the Taurai case, I think there are some is already some results, like by Nam Seiderman. This studies 3-body interaction many body problem in the waveguides in the periodic setting.
Okay, any further questions for speaker? Doesn't seem to be the case, so let's thank Professor Zhao again.
Thank you.
Well, thank you. For the
Okay.
talk.
Thank you.
I hope you could hear people clapping.
Okay.